Welcome to this session. This session is going to deal with boiling. First, let us see latent heat of vaporization. Latent heat of vaporization is a physical property of a substance. It is defined as the heat required to change 1 mole of liquid at its boiling point under standard atmospheric pressure. It is expressed in kilogram per mole or kilojoule per kg. The heat of vaporization of water is about 2260 kilojoule per kg, which is equal to 40.8 kilojoule per mole. This is called latent heat of vaporization. Now, let us see boiling point. The boiling point of a liquid varies depending upon the surrounding environmental pressure. A liquid in a partial vacuum has a lowering boiling point. Then, when that liquid is at atmospheric pressure, liquid at a higher pressure has a higher boiling point. The liquid is at lower pressure has a lower boiling point. We are going to see the types of boiling. Pool boiling occurs when a pool of liquid is heated from below through a horizontal surface. In pool boiling, the motion near the surface is primarily due to the natural convection. This is the phenomena which occurs in pool boiling. Now let us see a second category of boiling. It is flow boiling. Flow boiling is also called forced convection boiling. Fluid flow is forced over a surface by external means such as pump as well as by buoyancy effects. Therefore, flow boiling always accompanied by other convection effects. Conditions depend strongly on geometry, which may involve external flow over heated plates and cylinders and internal flow. In nuclear reactors, most of the boiling regimes are just forced convection boiling. Now let us see the classification of boiling with respect to the saturation temperature. Natural convection boiling occurs less than 5 degrees Celsius of delta T saturation. Similarly, above 5 degrees Celsius and within 30 degrees Celsius of saturation temperature difference, delta Tsat, nucleate boiling occurs. Transition boiling occurs greater than 30 degrees Celsius and less than 200 degrees Celsius. Finally, film boiling occurs. T saturation is greater than 200 degrees Celsius. This is a classification of boiling. Now we are going to see natural convection boiling. In thermodynamics, the requirement of boiling for pure substances to occur is that T wall is equal to T saturation. But in real experiments, boiling does not occur until the liquid is heated a few degrees above the saturation temperature. The surface temperature must be somewhat above the saturation temperature in order to sustain vapor formation. In this boiling mode, vapor will be observed over the water surface, but usually no bubbles will be observed. Next is nucleate boiling. The most common type of local boiling encountered in nuclear facilities is nucleate boiling. In nucleate boiling, steam bubbles form at the heat transfer surface and then break away and are carried into the main stream of fluid. Such movement enhances heat transfer because the heat generated at the surface is carried directly into fluid stream. Next, we are going to see transition boiling. The nucleate boiling heat flux cannot be increased indefinitely. At some value, we can call it as critical heat flux. The steam produced can form an insulating layer over the surface, which in turn reduces the heat transfer coefficient. This is because a large fraction of surface is covered by a vapor film, which acts as an thermal insulation due to the lower thermal conductivity of vapor relative to that of the liquid. And next we are going to see film boiling. A further increase in the heat flux causes a film of vapor to cover the surface. This significantly reduces the convection coefficient since the vapor layer has a significantly lower heat transfer ability. As a result, the excess temperature shoots up to a very high value. This is called film boiling. Next, we are going to see what is meant by thermal boundary layer. This session explains some parameters used to characterize the property of the thermal boundary layer formed by a heated or cooled fluid moving along a heated or cooled wall. In many ways, the thermal boundary layer description parallels to the velocity boundary layer in fluid mechanics. Consider a fluid of uniform temperature and a velocity impinging onto the stationary plate uniformly heated to a temperature. Let us assume the flow and the plate are semi-infinite in the positive or negative direction perpendicular to the plane. As the fluid flows along the wall, the fluid at the wall surface satisfies no slip boundary condition and has a zero velocity. These are some assumptions. But as you move away from the wall, the velocity of a fluid asymptotically approaches to the free stream velocity. The temperature at the solid wall is gradually changes to as one moves towards the free stream of the fluid. It is impossible to define a sharp point at which the thermal boundary layer fluid or the velocity boundary layer fluid becomes the free stream. Yet, these layers have a well-defined characteristic thickness. This is the concept of thermal boundary layer.